Welcome to the world of thermodynamics. This is the branch of physics that governs everything from the flickering of a candle to the massive engines of starships, studying how energy changes form. To understand how heat moves, we must first define our boundaries. In thermodynamics, we look at the system, the specific thing we are studying, and the surroundings, which is everything else in the universe. Systems come in three types. Open systems can exchange both matter and energy with the outside. Closed systems can exchange energy but keep their matter locked inside. Isolated systems cannot exchange either one. Let us begin our journey with the Zeroth Law of thermodynamics. It sounds simple, but it establishes our fundamental understanding of temperature and thermal equilibrium. The Zeroth Law states that if System A is in thermal equilibrium with System B, and System B is in equilibrium with System C, then A and C must also be in equilibrium with each other. This law is the reason thermometers actually work. When a thermometer touches your body, it reaches the same temperature as you, allowing us to read a reliable numerical value. Now we step up to the first law of thermodynamics, also known as the law of conservation of energy. It declares that energy cannot be created out of nothing, nor can it be destroyed. The total energy in an isolated universe remains completely constant. Energy can only change its face, transforming from potential, to kinetic, to chemical, or into heat. Mathematically, we write this as delta U equals Q minus W. This means the change in a system's internal energy equals the heat added to it minus the work done by it. Imagine a piston inside a metallic cylinder filled with gas. When we heat the gas underneath, the molecules move violently, causing the piston to push upward and lift a heavy weight. The heat we provided did not vanish. Part of it increased the internal energy and temperature of the gas, while the rest was converted directly into mechanical work to lift that weight. This brings us to a crucial question. Can we build a perfect engine that takes heat and converts 100% of it into useful work without wasting a single drop of energy? The harsh reality of nature says no. This brings us to the famous second law of thermodynamics, which introduces a concept that dictates the arrow of time. Entropy. Entropy is a measure of molecular disorder or randomness within a system. Nature naturally moves from highly ordered states to chaotic, disordered states. You can easily shatter a mug, but you will never see those scattered fragments spontaneously gather themselves off the floor and jump back together into a perfect cup. The second law states that the total entropy of an isolated system always increases over time. Heat will naturally flow from a hot object to a cold object, never the reverse on its own. To reverse this natural flow, like keeping the inside of your refrigerator cold, you must constantly input external mechanical work and electrical energy from a power grid. Because of entropy, no heat engine can ever be completely efficient. Some energy is always lost as waste heat to the surroundings, a principle proved by Sadi-Carnot. Next, we push things to the ultimate extreme with the third law of thermodynamics. This law looks at what happens when we remove almost all energy from a system. The third law states that as the temperature of a pure crystalline substance approaches absolute zero, or 0 Kelvin, its entropy approaches a perfectly constant minimum value of 0. Absolute zero is equal to minus 273.15 degrees Celsius. At this temperature, all classical molecular motion stops entirely. However, the third law also implies that it is physically impossible to reach absolute zero in a finite number of steps. We can get incredibly close, but never touch it. Let us look at thermodynamic processes. First, we have an isothermal process, where temperature remains completely constant. It must happen slowly, allowing heat exchange with surroundings. For a process to be truly isothermal, it must happen incredibly slowly, allowing the system to constantly exchange heat with its surroundings to maintain its temperature balance. Next is an isobaric process, where the pressure of the system stays completely constant throughout the change. A PV diagram shows a horizontal line. Think of boiling water in an open pot on your stove. As liquid turns to gas, the volume expands massively, but the pressure remains fixed to the surrounding atmospheric pressure. Then we have an isochoric process, where the total volume of the system cannot change at all. Because the volume is locked, the system can do no mechanical work. Imagine heating a rigid, heavy steel box filled with gas. The pressure and temperature skyrocket wildly, but since the walls cannot move, no physical work is performed. Finally, we encounter the adiabatic process. In an adiabatic change, no heat is allowed to enter or leave the system. The insulation is absolute, or the process happens instantly. A great real-world example of an adiabatic process is using a simple aerosol spray can. When you press the nozzle, the gas expands so rapidly that it does not have time to absorb heat. As the gas expands adiabatically, it uses its own internal energy to do the work of escaping, causing the temperature of the remaining gas inside the can to drop instantly. Together these processes form cycles that power human civilization. The most famous theoretical cycle is the Carnot cycle, which establishes the maximum efficiency limit for engines. By understanding thermodynamics, engineers built steam trains, modern automobiles, massive jet engines, and the giant cooling facilities that keep our internet servers running. From the Zeroth Law defining temperature, to the first protecting energy, the second driving chaos, and the third establishing the absolute cold limit, thermodynamics rules our world. Thank you for exploring the fundamental laws of heat, work, and energy.